mute all the microphones? Except for mine and
Yeah,
Nick.
I will. Let me go through and do that. Yep.
Thank you. Okay, so we have a real treat tonight. Dr. Nic Scott was a lead research scientist at NASA Ames Research Center working on exoplanets validation and characterization, and is now at the telescope systems the telescope systems scientist at the Center for High Angular Resolution Astronomy, otherwise known as CHARA Array. He lived in San Francisco Bay Area for 5 years and now resides in LA. Prior to coming to work at NASA, he worked for the Georgia State University at the CHARA Array on Mount Wilson, just outside of Los Angeles. His specialties are instrumentation, ground-based telescopes, high angular resolution techniques, interferometry, and exoplanets. He finished his PhD from GSU in 2015 and also received, I want to make sure I don't butcher this too bad, Kututele doctorate from the Paris Observatory during 2015 also. His current work is on interferometric detection of exozodiacal light around nearby stars. This is hot dust around the nearby stars. And he is also part of the Speckle Imaging Group that follow up on space-based detections of exoplanets. He's helped build and install 3 of these Speckle cameras on Hawaii, in Chile, and Arizona. Ladies and gentlemen, please welcome Nic Scott.
Yeah, thanks, Fred. Happy to be here. Happy to see everyone. Most of what I'm going to talk about today is the Speckle work and why we're interested in it, why we do it. I've got basically a crash course in exoplanets. So more than you could probably want to know about exoplanets. So let's go through, see if I can get my screen shared. Okay, so it's a fascinating time to be doing astronomy in that we're living through a golden age. You know, we went from the first exoplanet being discovered in 1995 to now knowing that the galaxy is just full of them, that they're commonplace. So what we want to do is understand as much as we can about them. So first off, what is a planet and what's an exoplanet? This seems like a trivial question, but it's actually pretty challenging. Several years ago, I'm sure you all know about the Pluto debate and Pluto, whether it's a planet or not. The International Astronomical Union came up with this definition that planets have to orbit the sun. They have to be big enough that gravity makes them spherical, and they have to clear their orbits of other material, so they're the largest body near their orbit. That last one may be confusing because what does that even really mean? It's a kind of a hand-wavy definition, but it's as good as we got right now. And what I like about this definition, for whether you're on the pro-Pluto or anti-Pluto side, is that it does break our solar system down into 4 terrestrial planets, 2 gas giants, and 2 ice balls, 2 ice giants. So it kind of separates them by category. And what we're trying to do and get toward is being able to do the same for exoplanets. So what's an exoplanet? All of the same things except the first one. It doesn't orbit the sun. So anything that if it was anything that's a large spherical rocky body going around another star than the sun. So we're trying to figure out what is our solar system. The original question was, is our solar system unique in that we know we have planets in our solar system? Do other stars have planets in theirs? And we now know the answer that yeah, planets are very common in the galaxy. And on average, every star has a planet. Some have none, some have many, but we know that planets and stellar systems are common. And we're at the stage now where we can start to categorize the different types of exoplanet. And what we're finding is that the exoplanets are far stranger than we would have imagined initially. And that whether our solar system is unique or not is still kind of a pending question. But we're finding things that are, the goal is to find exo-Earths, so other Earths around other stars. But in the course of trying to discover these, the first exoplanets discovered were these other gas giants, so Jupiter's and Saturn-like planets. And what was surprising is that these exoplanets, the first ones discovered, were giant hot Jupiters And they're basically, if you took Jupiter and brought it much closer to the sun, and these were the easiest ones to discover. And it's now we're looking at lots of like Neptune light and super Earths, which is basically very massive Earths. So we're finding types of planets that we, super Earths, we have nothing to compare them to. We don't know much about them because we don't have anything like that in our solar system. So the question is, how do we find an exoplanet? And the best analogy for this is that you're on a coast in the fog, looking at a lighthouse from say 10, 20 miles away, and you want to look and see a firefly right next to the lighthouse lamp. It's a contrast problem. It's an angular resolution problem, and it's a contrast problem because you're looking at on the order of 1 part in 10 million to 1 part in 10 billion is the level of contrast. So it's really an incredible challenge for even the best telescopes on Earth. So all we have is light from the star. We can't, in most cases, detect any of the light directly from the planet, but we have a lot of things that we can measure from the star, from the light itself. So we have the flux, we have the amount of light, we can get spectra, we can measure the position of the star, and we can tell something about the wavefront, the quality of the light itself. So this slide is kind of overwhelmed, but it's kind of the point is that just because all we can measure is light from the star, there's a lot of things that we can tease out from that. And that's where the science is, and that's what a lot of astronomy is kind of broken down into. Is we can look at the intensity of the light and use that to give us clues to exoplanets. We can look at the color and the spectrum of light to both find exoplanets and tell us something about what those exoplanets are made of. And I'll talk more about that later. And then there's other aspects. Polarization can tell us about the environment around the star. The polarization of light tells us, is the stellar environment dusty or not? We can also look at timing variations and how the light comes, and that can also clue us into whether there's exoplanets. So basically, you have to do incredibly clever detective work to try and find these exoplanets because it's just such a challenge. So I'm gonna go through a little bit of the methods. Transits are what the Kepler spacecraft and K2 and TESS use, and it's very simple. It relies entirely on a chance alignment, but we luckily have a whole lot of stars in the galaxy. And if the orbit of the planet is lined up so that the planet crosses the face of the star, and you monitor very carefully how bright that star is, you'll get a transit, just like Venus transit around our solar system, and you'll see a dip in the amount of light when that exoplanet passes in front. And from that, by measuring repeated dips, you can find out the distance of the exoplanet from that star, and you can also find the ratio of the size, the covering area of the planet to the star, and it gives you some clue about the size of it. The trick in this is that the better we know the star, the better we know the planet. So it's a lot of stellar astronomy goes into finding exoplanets. The other common technique is radial velocity. So all of these techniques have pros and cons and strengths and weaknesses. Radial velocity is the wobble of the star because of the gravitational pull of the planet. So it's sort of a two ice skaters grabbing hands and spinning each other. And just even though the exoplanet is much smaller than the star, it's going to impart this velocity, and this happens in the direction that we're looking at the star. We see the star move toward us and away from us, and you get a Doppler shift. And current instruments that measure this to try and find exoplanets are able to detect a movement of 10 centimeters per second. So a slower than walking pace of a star moving back and forth. So it's just an incredible amount of precision. And there's a lot of instruments that are spectrographs being built and currently operating that focus on this. Astrometry has not found as many. So those two techniques are the ones that found most of the exoplanets we know of. Astrometry is very simple. It's similar to the radial velocity, except instead of looking in the same direction, the wobble of the star going in and out, you're looking kind of down on the plane of the orbit, and you see the star wobble. And relative to other stars, you notice the position change. And so we can't directly tell the planet is there, but we can watch the wobble of the star and infer that there's an exoplanet. So this works better with the hotter stars and nearby stars, but it requires an incredible precision. So this is sub micro arcsecond position measurement. So that level of precision is equivalent to seeing something that's 1 millimeter on the moon from Earth. And then you get some really weird techniques that are, that work. And one of them is gravitational microlensing. It's also a chance alignment, but because the gravity of the star and its planet bends light from another star, it acts as a lens. And you get a little spike, you can see in the bottom corner there, that little spike in the amount of light that makes it brighter is the light bent by the exoplanet that causes it to focus as if it was a lens. And you can see from that, you can get that there is an exoplanet around the star. The downside of this technique is it's not repeatable. You've got this chance alignment that the star happens to go across a background source, and you get this focusing of the light. You measure it, you get this very distinct curve that follows the prediction, and then you have to wait, and it will likely never cross in front of with another source behind it again. But there have been exoplanets detected using this method. And then you can directly image. The challenge here is blocking out the light of the star. And so if you're looking, you've got two types of light you can look at. You can look at the visible light, that's the light reflected off the exoplanet that comes from the star, bounces off the exoplanet, and you detect that. But then you need a contrast of 1 in 10 billion. Or if you can block out the star and you look in the infrared, you can look for the light that's actually being emitted by the exoplanet. So all the planets, including our solar system, glow in the infrared. And then your contrast, you only need 1 part in 10 million. So it's still an incredible challenge, but it is, there have been exoplanets detected this way. So that's kind of all of the techniques and quickly brief overview of how we look for exoplanets. And the point here is that with all these different techniques, and there's some others, they all work together. They all have strengths and weaknesses, and they all can tell you more about the environment, and they kind of all have to work in harmony. You can get the radius of the exoplanet by a transit, but you can get the mass with the radial velocity or astrometry, and with spectra you can get potentially the atmosphere composition. So we want to know if the planet has an atmosphere or not, and that's kind of where in recent years what's happening in the science is looking at detecting what the temperature of the atmosphere is and what elements are in it. Does it have water vapor in its atmosphere? And this is kind of the cutting edge of where we're at in the field. So that brings us to, as of last week, I pulled this up. There's 4,400 confirmed exoplanets out of 7,600 candidates. So the confirming the exoplanets is part of what I work on, as well as characterizing the system. So I don't directly study exoplanets, but I study the stars that are thought to be hosts of exoplanets. And this tells you 75% of them are from the transit method. That's because we've had space telescopes that are specifically for this. I'll show you some of those, and about 20% with radial velocities, and then some with microlensing and imaging. So this gives you an idea. And the chart on the right tells you the period, so the length of the year versus the mass of the planet, and kind of a lot of what you're seeing there, this chart will be filled in as years go on, but you're also seeing a selection effect because of the different techniques favor, a transit's going to favor a bigger diameter planet closer to its star, because it's going to block out more of the light of the star, and you'll see the transit easier, as opposed to and the alignment will be more common, as opposed to a tiny planet that's far away from its star. There's less of a chance that it'll be aligned in such a way that we see that shadow. Likewise, radial velocity is going to favor ones that are massive, that pull on their star more and give you that velocity. So radial velocity measurements will favor planets that are big and close to their star. So all these things have to kind of have their niche. And by the way, this is at the exoplanets.nasa.gov. You can go and play with it and produce a whole bunch of charts. You can see how it updates and kind of see how it's going. This is also, this chart just shows a similar sort of thing, but just shows how it's changed over the years. So the first exoplanet was confirmed in 1995, and even then it was kind of questionable. And you see, it's just the initial ones were all the radio velocity technique, and then transits just taking off. And a lot of that's from the space telescopes. The reason you need a space telescope for the transits is to get the precision and the photometry, the measurement of the light. So, and you know, the holy grail of this is to find other Earths. And so these are lists of potentially habitable exoplanets. And by habitable in this definition is that we think it's in the region where liquid water could exist. Very, very basic definition of habitable. But if you notice the top left one on there is our closest star other than the sun now is known to have an exoplanet. So Proxima Centauri b, only 4.2 light years away. So that's really impactful and kind of exciting. So that's the basic overview of the science of how the different techniques and different teams of astronomers all work on these, kind of pick their instruments and work with that. I want to show a little bit of, this is my general public talk, just to the facilities we work at. This is what everyone always pictures, that we're Hubble looking through an eyepiece at the 100-inch telescope on Mount Wilson, which is an excellent experience to have. But really most of the work is somewhere like this. This is the Gemini telescope. This is where one of the spectral instruments I work on is at. So this is, I believe this one is Gemini North. Yeah, it looks like Keck through the background there. So this is an 8-meter telescope. The primary mirror is like an f1.8, and the total system is like an f16. Absolutely beautiful machine, and it has a twin in Chile. That's the Gemini South telescope. So 2 identical telescopes, 1 in each hemisphere. So really excellent to put twin instruments on. This is the site. So this is the astronomer's heaven. And this is top of Mauna Kea, a place that post-pandemic I'll be happy to go back to, but it is a phenomenal place. And I love this picture because in the background, you can actually see the shadow of the summit of Mauna Kea on the clouds. So 14,000 feet. I've been up there with snow in Hawaii. You can always pick out astronomers on the airplane to Hawaii because they're the ones wearing the big heavy jackets because they don't want to pack them in their luggage. Everyone else in the Hawaiian shirts and bridal parties and stuff like that. And the astronomers are all in parkas. So it's a incredible facility to work at. You can see the Keck telescopes there, and Gemini's in the background. It's the Silver Dome. Just for a sense of scale of this telescope, this is how it opens up, and you see the cement truck from its construction for scale for the size of this facility. Absolutely amazing instrument. And most of the time now, it's even when we go out to Hawaii, we don't typically observe from the summit. This is the base facility in Hilo, or we have a similar one in La Serena. There's still day crew that goes up and instrument work that happens, and you'll go for the summit for that. But typically just for comfort and ease of sleep and not having to go up, spend a lot of time in altitude. 14,000 feet is incredibly hard on the body. And quite a few people usually have to have oxygen while they're up there. You work for this one's from Hilo, so you work at sea level. You spend all night in a nice facility with a good coffee machine and look at a whole lot of monitors. So long past the days of photographic plates and eyepieces, it's still best to be able to go out to Hawaii and be able to take data there. So shifting gears a little bit, this is kind of the menagerie of instruments that work on exoplanet missions for the US anyway. So this is ground telescopes that have NASA participation. If you're a ground telescope, you're typically funded by the National Science Foundation. NASA does not do ground telescopes, except when it does. NASA helps fund ground telescopes only in support of space missions. So that's what's funded my project. That's part of the NN Explorer, the Large Binocular Telescope Interferometer, and the Keck Observatory. So NASA doesn't do ground telescopes except when it does. They favor the space missions, obviously. So Hubble, Spitzer, Kepler, and K2. TESS is now currently operating, and hopefully we'll soon see the launch of JWST and WFIRST. And then there's also partners with Europe, where Kourou and Gaia and Cheops and Plato Eventually there'll be future large space telescopes, hopefully. So these are all not solely exoplanet missions, but a key part of these different observatories is work on exoplanets. Just to give you an idea of the scale of these space telescopes, Hubble there with a person beside it, Kepler above it, and then TESS is the other one I'll talk about. TESS is the more recent transit exoplanet survey satellite, and then the JWST for comparison. So to give you an idea, the TESS is actually a pretty series of small cameras. And this is, you see the bottom, the guy in the bunny suit is looking at the CCD array for the Kepler Space Telescope. So this is the mission that was looking for transits. And so since transits rely on these chance alignments of happening to be looking in the direction of a star and the exoplanet crossing it across the face of the star, you build your telescope to have an incredibly wide field of view and look at a whole bunch of stars at once. And what Kepler was designed to do was stare at the constellation Lyra, a part of it. You can see the bottom right, I've got the CCD array highlighted on where it was looking in the sky, and just spend years looking at the same dense part of the sky and measure every one of these stars and monitor their brightness to a millimagnitude, much better than millimagnitude level of precision. So just how bright is this star for years, and hope to catch an exoplanet going in front of it. So it looked at over 100,000 stars for several years. And the top right, the little animated GIF we got there, shows you what one star looks like. So from a typical astronomy point of view, that's a terrible image. And it's not even an airy ring, it's just some pixels. But these are incredibly stable CCDs and a very stable system that you could then get the light curve. So plot out how bright the star is over time for years. And that's where the wealth of these exoplanets have been produced, the candidates have been produced. I won't say they're confirmed yet, because this is just to get the candidate list. The work that the ground-based follow-up that I work on is to chase this and try and see, is this really an exoplanet, and confirm that, and then what can we tell about it? So Kepler also just looked in one direction at, in this illustration, just kind of stared at this direction at Lyra and only saw a little ways out. It's around 3,000 light years. So not a lot of our galaxy, and was still able to find thousands of exoplanets. In fact, this is let me mute this, that they made an orrery of all the exoplanet systems that it found, and it categorized them by size, the orbit, and the temperature. And it's kind of gives you an idea of, like, compared to our solar system, there's a whole lot of variety in the types of stellar systems that we're finding. So it's turning out that, not only is our planet's common, but we've had a sample size of one solar system up until now. And now we're seeing that there's just this incredible range of types of planetary systems. So it's another case of reality being much more interesting than sci-fi in most cases. So the successor to Kepler is the TESS mission. So you can see the guys in the bunny suits for scale. This is a tinier telescope, but it's 4 cameras, and it looks at the whole sky. And it does this interesting pattern. You can see in the bottom right, where it takes a picture, I think it's every 28 days, and then shifts and takes another picture, and rotates and takes another picture. And it just keeps wrapping around the sky. And so you get this continual overlap zone at the poles, where you get a 351 day, where you can find a transit. So you can find the longer period planets, or you get more coverage on the other latitudes for that, roughly 30 day. And this is the first full image to come out of TESS. So this is actual data from that. And it's the same idea of all of these stars are looked at, you put boxes around them, and you look for how the brightness changes and hope that you catch a transit. So I keep saying that these are candidates, and we hope that we can confirm that they're exoplanets. The main reason that we have to do this confirmation is that it would be an exoplanet if it was small enough and the ratio was right, and you didn't have a binary system. Because what can happen is most stars aren't single. About half the stars you look at are actually binaries. About a quarter of them are triples. Is that if you have a star and it's in a binary system, that can create can mimic the signal you'd get from an exoplanet. So what we have to do is follow up and look at all these exoplanet candidates and see, is this a single star or is this a binary star? And that's what our ground-based follow-up does. That's what the instruments I built do. And to do that, we need, remember those pixels for a few pixels across the star to measure the light curve. You can't tell if there's a binary hidden in that pixel or not. So what you need is the opposite. You need, instead of having this wide angle instrument that looks at a whole lot of stars at once, we need a really high angular resolution instrument that looks at a single star very closely. This cartoon kind of sums up the same thing, that if it's just one star, you have a planet of a certain size, but if it's a binary, you may still have a planet, but that planet is much bigger than you thought. So now what you thought was an exo-Earth is now an exo-Jupiter, or maybe it's a small star and it's not a planet at all. And that gets even worse if the binary system is two different types of stars. And if you have the exoplanet going around the earlier type or the later type star, it's always going to make your exoplanet bigger, unfortunately. It never makes it smaller. So something can be an exoplanet candidate and then gets bumped out of being a candidate because it's actually a binary system, and either the binary was mimicking the signal or the exoplanet is now too large and it's just a dwarf star instead. So the problem, what we want to do to do this is high angular resolution, but the problem is the ground-based follow-up. The resolution of your telescope is dependent upon the size of the telescope, and all these space telescopes are small. So we need a really big telescope, and we don't have a really big telescope in space. We have big telescopes on the ground, but they suffer because of the atmosphere, which I'm sure all of you know as amateur astronomers, that the atmosphere is terrible, and it would be much better if we didn't have it, except for the breathing thing. So what we do is something called speckle. So this is data from the instrument I built. The top left is raw data. It's just, this is a star. It's frames taken every 60 milliseconds. So we take video of a star. The middle thing that turns to this yellow and now turning red is if you sum those up and like you did a long exposure photograph, like I'm sure many of you have with your astrographs. Instead of summing it up and taking a long exposure to try and get something faint, we look at a brighter star and we take these snapshots and then we combine them mathematically in Fourier space. And you get this thing on the top right, which is this fringe pattern. So it's an interferometric pattern. The starlight is actually interfering with itself, and you get this pattern. And by doing some more math on it, an inverse Fourier transform, you get the thing in the bottom, the middle right side here where there's two stars. So this is all data of the same object, and it's showing you the different ways you can look at it, and that this thing that is just these flickering blobs called a speckle pattern, if it is a binary star, when you do the math on it, you'll see it pop out, and we see that binary. And so in 1 minute of data, you see this star is actually a double instead of a single star. It's often confused. Some of you may have heard of lucky imaging. Lucky imaging does a similar thing of taking video and keeping the best images and throwing out the rest. This is not lucky imaging. Speckle keeps all of the data and does a lot more complex math on it. And from that math, you can get the binary. So it's incredibly efficient type of observing, and it can work in even pretty poor seeing conditions. As long as our seeing is less than about an arc second, you can see this is a pretty close binary, and this is something we can easily turn up. So you get the full diffraction limit of an 8-meter telescope by using this technique. This is myself and other people on my team, Steve Howell and Rachel Madsen. This is the instrument. It's unlike most astronomical instruments, professional astronomical instruments, because most of them are the size of like industrial freezers or small Volkswagens. This instrument fits on a tabletop. You see it's a small case size. The secret to it is mostly the cameras. These are electron multiplying CCD cameras. So each one of those is about they're $50,000 cameras each. They're little particle accelerators attached to a CCD. And what that does is give you an incredible amount of gain. So every photon gives a huge electrical signal. And that makes these cameras so sensitive that they can count single photons and operate at movie speeds. And so that's what we do. Here it is installed at I think this one's at Gemini South. So you can't even see the instrument because it's hidden behind those. The big blue crates are other instruments. So we're actually mounted between a calibration source for one of the instruments and the science fold mirror. So with that, we can then not only classify and validate exoplanets. We're not directly detecting the exoplanets, but we're looking at the star and telling if it's singular or double. And then with that information, you can feed backward into the detection parameters. And what we're finding is that there's all sorts of types of exoplanets. These are some posters that IPAC at Caltech put out that are these exoplanet travel posters, which I highly recommend people check out. But they're really fun, just showing the variety of types of exoplanets that have been found recently. One of the interesting things is this is a plot of the habitable zone. So that band of blue is basically, depending on the type of star, where liquid water could exist. And in our solar system, the habitable zone includes Mars and Venus. Unfortunately, they don't have water now, but they may have once had. And when you go to a smaller star, you see that the exoplanets might be closer in. And so we have this for every exoplanet we find. The better we know the star, the better we can then try and predict what type of environment that exoplanet might have and kind of focus our search. And the variety of things we're finding is, hot Jupiters, there are lava planets, there are ones that we know are made of molten rock. Rogue planets have been detected using that microlensing technique, where there's an exoplanet that doesn't have a star at all. It's been ejected, and those may be fairly common. Lots of really inhospitable planets, planets that are so close to their star, they're actually traversing the atmosphere of their star and evaporating in like giant comets. Really eccentric, strange orbits. Planets that might be, have huge oceans, and then planets going around stars that have long died. And one of the weird consequences of that, going back to that picture of the habitable zone being really close in to this red dwarf star, is that the planet might become tidally locked so that the same side is always facing its star. So you might get these planets that are either a desert on one side and frozen on the other, with a habitable in the sense of liquid water region around the terminator. Or if it's like a snowball Earth, you could have this like eyeball planet where there's an ocean under the hot spot and then frozen everywhere else. So systems that are incredibly different from what we're used to. Another finding that is that we found systems that have multiple habitable exoplanets in the habitable zone around a single star. And TRAPPIST-1 is an example of that, where you have tightly packed, roughly Earth-sized planets, all within a region where they could have liquid water. So it's a fascinating system. And because it's a small red dwarf star, it's actually packed in very, very close to the star, closer than the orbit of Mercury in our system. So just a great menagerie of stuff. And we've also found exoplanets going around a binary. So because binaries are so common, it's kind of not surprising that we found kind of every possibility of both a binary system with a planet going around one star or the other, or an exoplanet going around the pair as they orbit each other. So like Tatooine from Star Wars. And then we have this whole category of super Earths versus mini Neptunes. So planets that fit into the range of size between Earth and Neptune. And what that composition is, we don't know currently. We can figure out the compositions of these planets. We know that the compositions are very similar to the composition of their star and what elements may go into forming them. And so we're starting to try and work with planetary geologists to figure out, like, does it have plate tectonics? Does it have magnetic fields? Because these are important things for life. So if we want to find other Earths, we want to find places that maybe life could exist. These are the types of real details we're getting into. What's amazing to me about this is that if you go all the way back to the firefly around the lighthouse, we're really teasing out every bit of information we can. And just gives you an idea of, like, based on the composition and size of the planet, we're really looking at just differences in that shadow to tell if something is, coupled with also looking at spectra, whether the planet is, pure water, pure carbon, pure silicate, and there's error bars on all of this. We don't know exactly, but we can kind of get ideas of what the composition might be. It's really a huge amount of detective work. And that's why we build bigger and bigger telescopes and better instruments, because as we do that, get better data, we can actually start to draw real conclusions as to what these things may be made of. And this is just a nice image of like an exoplanet going around a pulsar, which is one of the stranger systems that's been found. So a long dead star, and the planet that was in that system survived that death of the star. And what we ultimately want to get to is not just looking at the exoplanet itself, but because you see this image that you can see the starlight through the atmosphere, that we could measure compounds within the atmosphere from the spectra. So if you have a sensitive enough spectrograph, a sensitive enough instrument, we could look for oxygen and methane and other biomarkers within the atmosphere. So there's a chance that we could discover good indicators of potentially life as like that we're familiar with around an exoplanet. And it all just comes down to looking at the spectra. So that's a really exciting thing of, can we find oxygen? Can we find compounds, more complicated, just from looking at that light from the star indirectly, the light as it's filtered by the atmosphere of this exoplanet. It's just the same thing I said. Wrapping up a little bit, getting into something really kind of fun is we could look at the star temperature. We could look at what compounds we find in the atmosphere and figure out where the peak frequency is of that light. And we can try and guess of like what might be, and this is getting into like speculation, obviously, but like on our planet, chlorophyll is the main source of the green and all that, and energy for life. Bacteria, there's types of bacteria that generate this purple compound. So we might be able to get signals of different colors and be able to trace it back of like, oh, that's from chlorophyll, that's from this bacterial compound, different pigments that life might use, and see just by looking at the color. And this is getting into a stretch, but we've come this far in the past 30 years, and another 30, this may be the type of science we're looking at, is trying to determine, what color are the plants on this exoplanet. All from looking at very, very tiny scales and a lot of precision. So just, I think my last slide is next. To just talk about where we've come from. Giordano Bruno, first proposed that there might be other planets around distant suns and that they might have life of their own, and that this is not so outlandish to think that if the universe is so large that there could be other worlds. And in 1593, he was tried for heresy and burned at the stake. But in 1995, it turned out he was right. So we've come a long way since then, and since 1995, this science has really taken off. That's it. And I can give you guys the link to my slideshow, and you can go back through, and I've got links for most of the material I've shown here. And I'm happy to take any questions you guys have. I know I went through quite a bit pretty quick.
Nick, that was awesome. What a great talk. Any questions for Dr. Scott, Nic Scott?
Yeah, I've got, actually, I think you pretty much did answer it as far as getting the spectroscopy out of the atmospheres. You're thinking within 30 years?
Hopefully less. I mean, we've got spectrographs that are now 10 centimeter and soon like 1 centimeter per second precision. And you just need the right sensitivity. And if we could put a big telescope in space with these instruments, I think it's possible. I'm not a spectroscopist though, so I focus on the ground-based high angular resolution follow-up. So I can easily say, sure, I don't want to do it, but someone could.
So are we going to need a space-based telescope to get this a clean spectroscopy out of that stuff, or can we do it from Earth?
I don't know. I would have said we would, but one of the things that's enabled this like centimeter per second from the ground, which 20 years ago someone said was completely impossible, is doing things. It's your calibration. And what they use now for calibration, instead of like a calibration lamp for the spectrograph, is laser combs and very
Right.
high precision, high stability lasers. So I don't know what the limiting factor is on that, but I imagine that if you get the calibration good enough, I don't see why not.
Okay.
Eric, you had a question.
Yeah, from that image with the habitable zone, I was just curious if you're at all able to infer the actual orientation of the orbitable plane of these other star systems.
Depends on the technique in which it was discovered. With radial velocity, you always have an ambiguity. It's a sine I problem. So the inclination, you find a minimum, and you can't directly tell, right? Because if you're looking at the Doppler shift of the star, you're not going to be able to know, is it the inclination of the orbit. Whereas with transits, you know that you're pretty much edge on. With astrometry, you can kind of work out. So if you use multiple methods, you can, or it depends on which method you started with. But radial velocity is one that's kind of plagued by this sine inclination problem. But with the habitable zone part, we just kind of, I think that's usually assumes a circular orbit. You can kind of, in ones where we have, know the eccentricity of the orbit, you can put it in and figure out. One of the things I'm fascinated by is you could have a planet that passes for some period of its orbit through the habitable zone. And what would life on that look like, right? What if we had a life on something like a comet, where instead of spending days going through the habitable zone, it spends months or years, and could you develop life where it hibernates while the exoplanet's at apogee or aphelion?
So we have a question from Mike and Jeff.
Oh, hi. Hey, really enjoyed your talk, but I'm looking at, like right now, we've looked at 4,400 planets, and honestly, zero chance that there's any civilizations on them. But I see where you're going to be looking at atmospheres and their spectra subtracted from the solar spectra. And we're going to be able to do this 2,000 light years away, maybe 22,000 light years away. And somewhere along the way, you're going to find industrial gases in something 20,000 light years away and say, dude, there's some people over there. Is that kind of one of the plans?
I know that if you look at like the SETI project, this is all what SETI is about. And I won't say that within those thousands that there's not life, whether it's industrial or not. I am of the, in the taking off my scientist hat, putting on my speculative fiction hat, I think life's probably really common. I think it's a chemical process that's likely. Whether it gets to the point of industrial civilization, I think that's probably way less likely. We have a sample size of 1-ish that we know. So it's a small sample size problem. So I don't make any probabilities. One of the questions would be, if we're looking at with Kepler, we're looking at a very small part of the space. We're seeing huge numbers of planets. Just the odds are that I would think there'd be something, but then the question becomes like, one, we don't have the capability yet to detect something. Even if there was any of these, if they had an industrial civilization, we couldn't tell you yet. Two, the bigger like species level question for me is, if there is intelligent life, does it survive industrial evolution? And that we don't have enough data of our own planet yet, so I don't know about other ones.
Yeah, they're 20,000 light years away. They could be long dead by now from their industrialization.
Yeah.
And the other thing is these that we've discovered, for example, Kepler with one of the occulting event, that's such a small percentage of the stars with planets would even have occulting events, and we're missing 99% of those darn things.
Yep, and there's a lot of work of doing all the math and the probability of if we, in this huge sample. So a lot of the work is doing control samples to then do the proper statistics to figure out that on average there's a planet per star, and that's where that number comes from. Is that based on because it's a geometric probability for the alignment. So we can work out what chance that is. And then you can work back out, well, of the alignments, we found this many planets. So you can kind of figure out that, yep, it is on average a planet per star. It's kind of a safe ballpark.
So we had Jeff Marcy here from Berkeley. And one of the things that they said 10 years ago was that half the stars in a galaxy are doubles. And what he was saying was, if a star is a single, extremely high probability it's got planets. If a star is double, kind of a low probability it has planets.
We don't know,
if that's changed.
That's still under debate. There's not, if I'm recalling correctly, there's not good evidence that being in a binary suppresses the likelihood that there's a planet. What you get is a selection problem that most people hunting for planets avoid binaries because the exact problem I said of it makes it complicated. So I don't think that being in a binary system actually suppresses planetary formation. And we are finding planets in binary systems now. It's just typically when you're doing planet hunting, you take all the binaries off your list because you know that it's going to be hard to prove there's a planet there. So especially in the early days, that was how it was done.
Nick, I have a couple of questions.
Sure.
Number one, being an amateur and budding spectroscopist with my instruments in the backyard, when you get information to look at a star that is potential exoplanet candidate, is there one particular or sections of the spectrum which you start with, or is there, like a sweet spot, so to speak?
I don't really do spectroscopy, but we do follow up for the spectra, the radial velocities. So our follow up is mostly to confirm that the star is single or binary. The main thing that is a hindrance that'll fool you in thinking you found an exoplanet is that you find out that actually it's a binary. And because if you think it's just that light curve and it dropping, or in radial velocity, it could be a binary system that gives you a signal.
Oh, okay.
Yeah.
So that actually leads into my second question in regarding to speckle. There's a lot of us that have got imaging processing software, that does stacking and wavelets and all number of things like that. When the speckle camera runs, does it do the onboard processing real time, or do you have to take the data and then massage it?
We don't currently. There's nothing preventing us rewriting our pipeline other than it's a monumental effort we use a pipeline that was developed by one member of our team like 10 years ago. Mm-hmm. So mostly no one's taken on the effort to modernize the code so that it could be done in real time. But that image stack I showed you of it, changing over time. Yeah. Conceivably with modern processing, we could. Usually we just do it over one of our team is on day shift and does the data processing during the day while the rest of us sleep. But conceivably it could be done real time. Conceivably this could be done if you have a good enough camera. You could do it. It's just a lot of math.
It was really fascinating to watch the evolution of the image coming out. I know when I'll take an image of Jupiter or Saturn, and you look at the video and it's kind of this oscillating mass,
What you could do is you can do speckle without doing the analysis and the reconstructed image is the tricky part, making a real image out of interference pattern. Mm-hmm. What you can do, and if you take a binary that's a close binary, like near your diffraction limit of your telescope, and you're in video mode, and you get a kind of an eye for interferometry, you can see the speckle pattern. You can see the interference, those fringes in your image. So in real time at the telescope, if I look at a close binary, it'll kind of get like a lined pattern, or sometimes it looks almost like herringbone pattern where the speckles overlap, and you see it's a interference pattern, and just like the classic like two slit experiment of light interfering and you get constructive and destructive interference, you can see that in real time, and that's how it's a binary. So if you want to, if you get some of you guys have telescopes that are big enough and cameras that are fast enough, you can do this, and take a look, and you'll see like this weird pattern to the double star. But it's got to be good seeing, and it's got to be a close binary that's at or just a little bit further separated than your diffraction limit.
Got it. Well, good seeing in California is marginal at best right now.
Yeah. Helps if you have better than an arc second seeing.
Yeah, absolutely. Okay, other questions of Nick?
Are there any like city at home type of projects that amateur astronomers can help out with?
With the
For
exoplanets,
exoplanets? Yeah, for
absolutely. It's part of the Galaxy Zoo. Let me see if I can pull up the. Yeah, if you go to the Zooniverse and search for Galaxy Zoo, there's a whole bunch of stuff there's planet hunters for that. I'll put the link in the chat. So yeah, there's a lot with exoplanets. A friend of mine, Tabitha Boyajian, works on that. So yeah, you can absolutely. Humans are great at pattern hunting, and that's a good part of it.
Cool, thanks.
Mm-hmm.
Other questions of Nick? Anybody?
How close are we to finding exomoons at this point?
They have been found.
Oh, really?
Yeah,
Okay.
exomoons and exocomets have been found.
Ooh. Cool.
So
Very cool.
hard to characterize. It's right at the edge of it's a detection, but it's hard to tell as much about them. But yeah, exomoons and exocomets have been reported.
That's cool. I hadn't heard that.
Other questions of Nick?
Yeah, I hate to keep hogging this, but I got to ask you about that last thing. If we were looking at the Earth pass in front of our sun, we'd see a double blip, one for the Earth, one for the Moon. Is that how you found moons?
That's how exomoons have been found. Yeah. Again, it's you can figure out the ratio, right? If you take the area, the ratio of the area of the sun to the area of the Earth, you get an idea of the signal, and then the ratio of the area of the Moon to that, you see why it's easy for it to get lost in the noise.
So now I'm kind of surprised we haven't found a lot of exomoons.
It's a very small signal.
Right.
Again, you'd have to be looking right at the right perspective to see the eclipse of it.
Yeah.
But as
Also most moons are pretty small.
That's what I say. As the instruments get more and more sensitive, we will probably end up picking up more and more of them then.
So
Nick, how many follow-ups do you do per year or over a given time frame?
So the nice thing about this is the main thing that funds this Speckle project that built these 3 instruments. The nice thing about this for follow-up is that Speckle is incredibly fast. So I showed you that movie that 1 minute of data. It really does operate pretty much that fast for a bright star. So we have to do a calibration source. So we look at a star that we know is a good point source. That's part of what needs to go into the data reduction. So we calibrate with a point source star from a catalog, and then we look at the science target, and we spend between 1 and 10 to 20 minutes on the science target. So we can get 100 targets done a night. So TESS is looking at these huge sections of the sky, and they get candidate lists that are thousands of stars long, and we get about every year we get about 40 nights or so at Gemini's. And so we go through about 100 targets on a good night. So we kind of keep pace with confirming or disproving these as we go.
Do you interface any with some of the Space Telescope people?
Not directly.
Okay.
It's mostly they publish. There's catalogs that are called TICs or KICS and TICs, which is Kepler input catalog, and TIC is the TESS input catalog. And then there's the candidate list that comes off that. And we, different principal investigators with our group will take that list and feed it into our target list for the night. So we were funded from NASA just to basically offer this instrument to the community. So people propose for time, goes through the proposal review process. The telescope allocation committee decides how much merit the project has and assigns how much time you get on sky. And so most of what we do is just service for the community to look at these targets.
My question was a little bit leading because we did have another NASA speaker here, Roberto Carlino from NASA Ames, and he had been working, well, the last time I talked with him, he had been working on TESS. So when you showed that was quite interesting.
Yeah.
Other questions?
I have a question that could come out sounding kind of dumb, but I got to ask it.
Mm-hmm.
Does anybody monitor some of the brighter stars in other galaxies with the possibility of an exoplanet occulting them, so get an extragalactic exoplanet.
Right. I don't think there's been any. I think someone's attempted that, but the way it works out is it's pretty unlikely we'd be able to detect it. I could be wrong, but I don't think one's been detected. I could be wrong.
That would be a cool record to set, though.
Yeah.
Other questions of Nick? Okay, Mike, turn it back to you. Thank you, Nick. Great.
Okay. Thanks, everyone.
Very
I'm going to
great.
log off. So, all right. Feel free to email me any other follow-up stuff. All right. Bye.
Thank you.
very much. That was excellent. Okay, well, guys, Jeff wants to say something, I think, and also the raffle.
Yeah, I got two things. One is the raffle, and one is he wasn't a member, but he was our friend, Buck Turgis in San Francisco, one of our ATM buddies. He passed away of pancreatic cancer, and his wife gave me about 150 pounds of astronomy or sky telescope and astronomy magazines, and I have to get rid of them. So on our last newsletter that we got from Jerry, there was a notification in there that said, hey, here's the magazine Jeff's got, and it listed all the years and months that I've got. So please, could somebody please take them? I got to get rid of them. And if not, I'll find good places to distribute them. But it'd be really great if a Stockton Astronomical Society member in need of some of these would be willing to take them. Email me off meeting here if you want to do that. The second thing is, Doug, congratulations. Here's what you won tonight.
Oh dear.
You won 3 things. An Astronomical League calendar that's already 8/12 over. A 75th
How
anniversary,
lucky.
75th anniversary lapel pin for the Astronomical League, and probably the best of it all, a refrigerator magnet Astronomical League emblem. Congratulations, Dougie.
Wow, I'm underwhelmed.
Yeah, we got those, and it's like, what do I do with this? Boom, door prize. Congratulations, Doug.
Try not to pass out. I know it's a lot to digest right now.
I know. I'm feeling so incredibly wealthy right now. Yeah.
I'll give them to you at Oak Grove Park Saturday night.
Well, you'll be there. That'll be great. And Mike, happy birthday.
Thank you. Thank you
Happy
very much.
birthday, Mike.
Oh, man, appreciates it.
85.
85.
85, man.
Oh, please, no. There's plenty of time for that. All right. Does anyone have anything, any business or anything popping up here that needs to be discussed or mentioned?
Just real quick.
A real quick one.
Go ahead, Fred.
Yeah, just a reminder, everybody on Luminous. I don't know if I stumbled through it bad enough, but it is a private viewing. You have to make reservations. You can reach out to Tim. Doug, I think you said you were going to take names also.
Yeah, I can do that. I just need to know the parameters of what how you guys want me to take names and so forth. So
Okay.
I would like to get some instruction on that before we get started.
Okay. So the intent is not to hinder or prevent people from coming. It's just that we have to control the access to the building.
Right.
We want to make sure that it's done in a professional, clean, and non-destructive manner, if you will.
Right.
I was actually going to look at trying to create some kind of online form on the website. So I'll see if I can't iron that out over the weekend.
Okay.
Sounds good.
That's all I got, Mike.
I've got one thing for Nihar. Nihar, unmute your mic there, buddy. Hey, on the astronomy badge for the merit badge, let your group know that we can do this, but it would be easiest if you guys came out to Oak Grove
Okay.
with what you guys need, and we will take care of it.
Yeah. Okay.
Any of your group that wants to work on their merit badge for astronomy, we can do this thing. It's going to take months to do it because there's a lot of things that have to be done, but it's a perfect place to do it all. And then you'll have plenty of help. Any of us guys that are out there would be glad to help any of your members earn that merit badge.
Yeah. Yeah, I can definitely set that up.
All right. Like I said, that was all I got.
Another comment, if I can, real quick, going back to the beginning of the meeting where we were mentioning the New Moon Challenge. Both the Word doc explaining the challenge and a Excel log sheet has already been posted to the SATS website, and you can find it under the resources page and then under the download section. So there's several links under the download section, but there's definitely 2 links there for both of those items. So if you're interested, check those out.
Sounds good.
Very good. All right, Eric, I got a question for you. On the background you've got there, there's your friendly dog digging in the moon. Has he found anything yet? Any bones or alien bones, anything like that?
No, he just seems to like that one spot right there.
Having a heck of a good time, I'll tell you that.
Jimmy Hoffa.
No, he's going to find that big black monolith.
There you go.
All right, anything else, folks?
Jim Hedrick, thanks for taking care of us.
Thank
tonight.
you, Jim. Yeah.
Thank you, Jim.
Yeah, Jim.
My pleasure as always. Great talk. Nice to see you guys again. By the way, just one quick announcement. So the physics department hired a new radio astronomer. He just arrived this summer. His name is Dusty Madison. He is a member of what's called the NanoGrav collaboration. They use pulsar timing to look for gravity waves. So I'm sure we'll pull him into the SAS and get him to give us a talk.
Is he available in
That'd be
October?
fantastic.
In October, I'll ask him. He gave a really, really great job talk. Really outstanding, great guy. So look forward to introducing him to you guys.
Great.
Great.
What is the current state of the radio telescope on the roof? Last week, I thought you guys were working on a new one.
Yeah, so we got a new a 4.5 meter dish, all ready to go. Students built a new superhead radio. It was all set to go. That we were just building the mount in March when lockdown happened, March 2020. It's all been sitting over there. I've snuck into the physics department a few times over the summer, and I got the Linux box to control the actuator that goes on top of the mount and controls the dish. But the dish is just sitting there. If you drive past Olson Hall, you can see it up against the chemistry building there, kind of against the wall. So as soon as we're back, and students will be back on campus next week, I'm hoping we can get a team and revive that, get it going again. It's kind of like, I've been over to the department. I don't know how it is for you guys who are going to school or work, but it's kind of like starting up an old car or an old boat that's been sitting for a couple of years, cobwebs in the office and stuff like that. It's good.
Very cool.
All right.
Good to see you guys.
Thank you again, Jim. Thank you very much. All right, folks. Anything else? Otherwise, we'll call the meeting to an end. Cool. Okay. Motion to adjourn.
So moved.
Second.
Okay, everyone, stay safe. Take care, and look forward to seeing you guys again soon.
Take care.
Here.
Hey,
See you later.
Good night, everybody.
Everybody.
Bye.
All right.